5.2, we're going to talk about Rolle's theorem and mean value theorem. So first we're going to talk about Rolle's theorem. So the first half is Rolle's theorem. So it says the extreme value theorem states that a continuous function on a closed interval must have both a minimum and maximum on the interval. This is what we did yesterday in 5.1, or the day before. Today, we're going to do Rolle's theorem, so it's kind of the same idea, just a little bit different. So it says both of these values, however, can occur at the endpoints. In Rolle's theorem, it gives conditions that guarantee the existence of an extreme value in the interior of a closed interval. So Rolle's theorem just says that we will have a max or minimum inside of our interval. So Rolle's theorem says let f be continuous on a closed interval and differentiable on the open interval, and f of a has to equal f of b. Then there's at least one number c in this interval such that the derivative equals 0. So this means that we have a horizontal tangent line. Which means that there's either maximum or minimum. So if I have two x values, a and b, and their y values are the same, so if I had 2 points up here, then at somewhere in between these 2 points, I have a maximum where I have a horizontal tangent line. Or I would have a minimum where I have a horizontal tangent line. So we'd either have a maximum or minimum depending on how our graph looks. So this page just says the same thing. From Rolle's theorem, you can see that a function f is continuous on a to b and differentiable on the open interval from a to b. If f of a equals f of b, there must be at least one x value between a and b, which the graph of f has a horizontal tangent line. So that would be where we have a maximum. Or if it dips down low, then we would have a minimum. It doesn't work. You can't apply Rolle's theorem if we have a sharp point on our graph, because at this value c, if it's a sharp point, it's not differentiable. So we can't use Rolle's theorem if it is not differentiable or if we have a sharp point. So we can't apply Rolle's theorem here. So an example one, we want to find the two x-intercepts of our function and show that f prime of x is equal to 0. So our derivative equals 0, which means that we have a horizontal tangent line at some point between the two x-intercepts. So let's find our two x-intercepts first. How would I find an x-intercept? Awesome. Set our function equal to 0. How would we solve here? Awesome. We factor. What are two factors of 2 that add to -3? -1 and -2, perfect. So we have x minus 1 and x minus 2 equals 0. So what's x going to equal? X can equal 1 and 2. Our x-intercepts are 1 and 2. Now we need to show that our derivative equals 0 at some point between the two x-intercepts. So we're looking between the two x-intercepts. So our interval that we're dealing with here is from positive 1 to 2. We get those from our x-intercepts. That gives us the interval. Now in order to use Rolle's theorem, we have to check 3 things. We need to make sure it's continuous. Is our graph continuous between 1 and 2? Is there any value that I can't plug into x here? No. What's the shape of our graph? A parabola. And we know that a parabola is continuous. So it is continuous. We need to know that it's differentiable between 1 and 2? So we can take the derivative. We're going to have to do it here. So let's find our derivative. What would our derivative be? 2x minus 3. Perfect. It's differentiable. We can take the derivative. We don't have a hole in it. And we need to make sure f of 1 is equal to f of 2. And those two numbers come from the endpoints there. If I plug in 1 into my original function, what do we get? If I plug it into my original function here, what do we get? 0. If I plug in 2 into my original function, 0. So is f of 1 equal to f of 2? Yes. So because these three things are true, we can use Rolle's theorem. So we know that there has to be a point in between these two numbers here, in between our interval, where our derivative equals 0. Camila, question?
How do you know it's continuous? Just because it's a parabola?
It wouldn't be continuous if you have like an asymptote or x on the bottom.
Oh, okay. And then
If you had a hole.
It's differentiable because you can take the derivative.
Yeah. And
Can you just take the derivative after?
yes, but then if you have like an x on the bottom, you have to be careful because it could be differentiable with a hole, so then it wouldn't be differentiable at that point. I think we're going to do, there's an example where it's not.
Okay.
I'll show you guys. So let's find where our maximum or minimum is. Because we know that because these three things are true, because it's continuous, it's differentiable, and f of 1 is equal to f of 2, that we do have some point that our derivative equals 0. So let's solve. I'm going to add 3 to both sides and divide by 2. What does x equal? 3 over 2. So this is our x value where we have a maximum or minimum. Let's draw it real quick. We have a point at 1, 2. These are our x-intercepts. Does our graph open up or open down? It opens up. So at 3/2, do we have a maximum or minimum? A minimum. That'd be our lowest point. We have a horizontal tangent line through there. So this would be our minimum. How do we find the y value for our minimum? We plug in the x value into what? The original equation. Awesome. So to find y, we plug in the x value. So we would find f of 3/2. And that would give us our minimum. Next page is just the solution to what we just did. So it draws it out for us. It shows us the x-intercepts. Because our x-intercepts are equal, it's continuous and differentiable, then we know that there is some minimum in between. And so we just found the minimum by setting our derivative equal to 0. So Rolle's theorem states that if f satisfies the conditions of the theorem, so our conditions are if it is continuous on the closed interval, I'll say from A to B, if it's differentiable on the open interval from A to B, and f of A is equal to f of B. So if these three conditions are true, then there must be at least one point between A and B which the derivative is 0. So if our derivative is 0, that means that we have a horizontal tangent line. Which means that we'll have a relative maximum or minimum. Let's look at example 2. Can Rolle's theorem be applied to this function? If so, find all the values C at which the derivative is 0. So here we got to be careful because we do have a fraction. So we want to figure out, is it continuous from -1 to 3? Is it differentiable from -1 to 3? And does f of -1 equal f of 3? So we have to check these three things. Well, let's see, is it continuous? Because we have an x in our denominator, what can x not equal? It can't equal -2. We'd set our denominator not equal to 0. X cannot be -2. So we do have either a whole or an asymptote here. But is -2 in our interval that we're looking at? No. So if our whole or our asymptote that we have here is not in the interval, are we continuous on this interval? Yes. So our function as a whole is not continuous, but from the interval from -1 to 3, we are continuous. Now we want to see, is it differentiable on this interval? So let's take the derivative. How would we take the derivative here? Low d high minus high d low over low squared, our quotient rule. So low would be x plus 2. The derivative of our numerator is 2x minus 2 minus high d low. So high would be x squared minus 2x minus 3. And then the derivative of our denominator is 1 over low squared. Let's simplify a little bit. We have to FOIL out the numerator. So we get 2x squared minus 2x plus 4x minus 4, and then distribute the negative here. Minus x squared plus x plus 3. So when we combine our like terms, we get x squared. This should be a 2. Negative 2x plus 2x would cancel, so plus 4x minus 1 over x plus 2 squared. So this would be our derivative. What value is our derivative? What value does our derivative not exist at? What x value can we not have here? -2. X cannot be -2 because we can't have 0 in the denominator. Is -2 on our interval? No. So is it differentiable? Yep. So it is continuous and it is differentiable. One last thing we have to check. Does f of -1 equal f of 3? So let's plug that in to find out. F of -1. We plug in -1, we get 1 plus 2 minus 3 over 1. So that would be 0 over 1, which is just 0. And then f of 3 would be 9 minus 6 minus 3 over 5. So we get 0 over 5, which is just 0. Does 0 equal 0? Yes. So f of -1 equals f of 3. So all three conditions are met. We can use Rolle's theorem. That was the first part of this question. Can Rolle's theorem be applied to this function? Yes. If so, find all the values of c at which the derivative is 0. What would we do next? Awesome. We want to find where our derivative is 0. So we'd set this equal to 0, but when it's a fraction, we really only care about the numerator. Just set the numerator equal to 0. If you want to set it equal to 0, multiply both sides by the denominator, it becomes 0. It's just a couple extra steps. But we just have to set the numerator equal to 0 and solve. So we get x squared plus 4x minus 1 equals 0. Can we factor this? No. So what do we do if it doesn't factor? Quadratic formula. Or you could complete the square. That would work too. Let's do the quadratic formula. Negative b, so -4 plus or minus the square root of b squared. So that would be 16 minus 4 times a times c over 2a. So 2 times 1 would be 2. So this would be negative 4 plus or minus the square root of 20 over 2. And the square root of 20 simplifies to 2 square root 5. Oops, this should be just 2. Can we simplify this anymore? How? All the whole numbers are divisible by 2, so we can divide them all by 2. So this would be negative 2 plus or minus square root 5. Now we have to be careful. At these two values, because we have two numbers here, negative 2 plus square root 5 and negative 2 minus square root 5, we have a horizontal tangent line. But we have to check, is it in our interval? A lot of these questions will give you two values, but it's not always that both of them are going to be in the interval. So let's see. Let's split it up. We have negative 2 plus square root 5 and negative 2 minus square root 5. Square root 5 is about what value? 2.1-ish. You could even say about 2-ish. How did you know that? Perfect. Square root of 4 is 2, so the square root of 5 is really close to the square root of 4. So it's going to be about 2-ish. So negative 2 plus 2-ish would be about 0-ish, we could say. Negative 2 minus 2-ish would be negative 4-ish. Are either one of these not in our interval? Negative 4-ish is not in our interval from negative 1 to 3. So this would not be a solution. So our only answer would be negative 2 plus square root 5. This is the c value or the x value at which the derivative is 0. If we wanted to find the exact point of where our maximum is or minimum, what would we do? How do we find the y value? You'd plug it back into the original. We're not going to do that here. We're just going to say this is our c value, which is the x value. So yesterday we talked about Rolle's theorem. Today we're going to talk about mean value theorem. Similar idea, but different. So if it says mean value theorem, we're going to use this formula here. Mean value theorem says, if our function's continuous on the closed interval and differentiable on the open interval, then there exists a number c from our interval a to b such that the derivative of c is equal to the slope from a to b. Bless you. So this is saying that the slope of the tangent line is equal to the slope of the secant line. On this page is just another example showing you that if we took the slope of the tangent of the secant line, so it goes through 2 points, we just find the slope of that. There's some point C, which is our x value, on our graph to where the tangent line will have the same slope. So they're parallel. So in order to use mean value theorem, we need to know that it's continuous on the closed interval and differentiable on the open interval. So is it continuous and is it differentiable? So here our function is f of x is equal to 5 minus 4 over x. What could x not be? 0. X can't be 0 because then that would give us undefined for our function. or it would have a asymptote there. Is 0 in the interval that we're looking at? No. So are we continuous on the interval from 1 to 4? Yes. To find out if it's differentiable, let's take the derivative and see if where we have an asymptote or where we have a hole is also not in our interval. So when we take the derivative, I'm going to change this because I don't really want to do the quotient rule. I'd rather make it a negative exponent. So I'm going to change it to be 5 minus 4 times x to the power of negative 1. Just because I would rather do this. It's going to be less work than doing the quotient rule. So when we find our derivative here, what's the derivative of 5? 0. So negative 4 times 1 would be 4x. When we subtract 1, we get to the power of negative 2. So this is like saying 4 over x squared. What could x not be here? 0. Is 0 in our interval? No, so we're good. It's differentiable on our interval. So next thing we need to do for mean value theorem is we need to see what value of c does our derivative equal the slope. So let's find the slope. When we find the slope, we're using the original function. Notice here how it's just f of 4 minus f of 1. You're using the original function to find the slope. So let's find f of 4. When we plug 4 in, we get 5 minus 4 over 4. So 5 minus 1 would be 4. F of 1 be 5 minus 4 over 1. So 5 minus 4 would be 1. So f of 4 would be 4 minus 1 over 4 minus 1. Give us 3 over 3, which is 1. So our slope of our secant line is 1. Now we want to see what value of x does our slope of the derivative equal 1. So I set my derivative equal to 1. So whatever the slope you get when you find the slope here, and you use the slope formula, you're going to set your derivative equal to that. And now we solve for x.
Wait, why don't we do this?
Mean value theorem. That's what we do.
And what are we trying to find?
We're trying to find what value of x gives us the same slope. So what value of c is what they call it here, is our slope equal to the slope formula. So when we solve, we get 4 equals x squared. Take the square root. So what does x equal? Plus or minus 2, but we always need to ask, is it in the interval? Is positive 2 and negative 2 in the interval? Which one's not in the interval? Negative 2, because we're looking at the interval from 1 to 4. So negative 2 is not in the interval, so it's just x equals positive 2. Next page is just the solution for example 3, the last question we did, so it draws it out for us. So we found the slope of the secant line using the slope formula. Then we had to find what point, what x value does our tangent line have the same slope. So find the slope, set your derivative equal to that, and solve for x. Let's do the same thing for example 4. It says apply the mean value theorem if possible. If it's applicable, find all such c values that f of c is equal to our slope. So we're given the function negative x squared plus 4 on the interval from negative 1 to 4. In order to use mean value theorem, we need to make sure that it's continuous and it's differentiable. Is our graph continuous here? Is there any x value that I can't plug in? No, it's a parabola, so it's continuous. Is it differentiable? Let's take the derivative and see what we get. So our derivative would be negative 2x. Is there any value I can't plug into x here? Nope, so it's differentiable. Perfect. So now we want to see what our slope is of our secant line. So we're going to use our interval here and find the slope. So we want to find f of 4 minus f of -1 over 4 minus -1. So we need to figure out what f of 4 is and what f of -1 is. So we're going to plug those in to our original function. When we plug in 4, we get 4 squared, which is 16. So -16 plus 4 would be -12. And then f of -1, -1 squared would be +1. Negative on the outside makes it -1 plus 4 would be 3. So this would be -12 minus 3 over 4 minus -1 turns into +1. So -15 over 5 would be -3. So this is our slope of our secant line. We need to set our tangent line equal to this slope. So our slope was -3. We're going to set our derivative equal to -3 and then solve for x. So when we solve for x here, what do we get? 3 over 2, perfect. Is 3 over 2 in our interval? Yes, so this is our value of c. Yes?
So if it's not in the interval, like say x is like 5, what would you, if it's not exist, or?
Yes, but because it's a theorem, so because it's mean value theorem, it says that there is a value for c in between this interval, so there has to be a number. So usually if you get 2 numbers, one of them may not work, one may. It is possible that they both work, so just,
One of them's always gonna be there?
yes, if mean value theorem applies, so if it's continuous and if it's differentiable, you will get a number. So we're doing the same thing for example 5. Apply the mean value theorem if possible. If it's applicable, find all such values where our slope of the tangent line equals slope of the secant line. So it gives us our function is x to the power of 2/3 on the interval from -1 to 2. So we want to see if we can use mean value theorem. We want to see, is it continuous? Is it differentiable? Is our function continuous from -1 to 2? Yes, it is. We can plug in -1, every number between -1 and 2, and get a value there. Let's take the derivative and see if it's differentiable. So we get 2/3 x to the power of, when we subtract 1, -1/3. So we can write this a little bit better. 2 over 3 times the cubed root of x. If you wanted to change it, you can leave it as x to the 1/3 power. It doesn't matter here. What could x not equal here? 0. Is 0 in our interval? Yes. So is this differentiable from the interval of -1 to 2? No. So it is not differentiable. So because x cannot equal 0 here, and 0 is in our interval, it's not differentiable at 0. So we cannot use mean value theorem. So because our derivative at 0 is undefined. All right, Let's do example 6. Apply the mean value theorem if possible. If it's applicable, find all such values that our slope of the tangent line equals the slope of the secant line. So we want to see, is it continuous and is it differentiable before we can start? Bless you. What shape of graph do we have here? A parabola. Is our parabola continuous from 0 to 1? Yes, so it is continuous. Let's check, is it differentiable? So let's take the derivative. When we take the derivative, we get 2x plus 2. Is it differentiable? Yes. All right, so now let's find our slope. So we're going to use our slope formula. We want to find f of 1 minus f of 0 over 1 minus 0. So f of 1, when we plug 1 in, we get 1 plus 2 minus 1, which would be 2. F of 0, we would get negative 1. So we plug everything in, we get 2 minus the negative 1 over 1. So this would be 3. What would we do next? We set our derivative equal to 3. So because our slope was 3 here, we set the derivative equal to 3, and we're going to solve for x. So we can subtract 2. 2x is equal to 1, divide by 2. What does x equal? 1/2. Is 1/2 in our interval? Yes.